So we can compare that to a situation where one of the sides is mixed, right? So what we just looked at was the case where both fluids are unmixed. So here's unmixed, right? We can't mix this fluid with this fluid. Mixed means there are no geometric obstructions. So there's nothing stopping the fluid from one side from mixing with the fluid on the other side. That's mixed. And if that's the case, then it's unlikely that you're going to develop a temperature gradient from one side to the other, because mixing is going to prevent that from happening, right? So this fluid here, let's say this is the hot fluid, it interacts with the cold fluid, and again, the flow over here is going to interact with the coldest of the cold fluid, and then the hot fluid over here is going to interact with the hottest of the hot fluid. But if I have mixing, then never am I allowed to have a temperature gradient in this direction perpendicular to the flow. So you can see the outcome of that is that, so in this case here, let me find my pointer. In this case here, I guess the cold fluid is mixed, and you can see as the cold fluid goes through here, it comes in at a uniform temperature, and as it moves through the heat exchanger, its temperature rises, but never is there a temperature gradient across the cold fluid, right? The hot fluid in this particular case must be unmixed, because you can see it comes in at a uniform temperature, but as it flows through the heat exchanger, I am allowing the hot fluid over here to be at a different temperature than the hot fluid over here. So that's what mixed and unmixed means, right? The idea of a cross-flow heat exchanger, I think, is pretty easy to understand. It's a little more subtle to understand what it means when you're looking at mixed versus mixed unmixed, or mixed unmixed, or those kind of things. And in the end, you know, your geometry dictates which type of situation you have, or at least which type of situation you're approaching. In reality, you won't get a pure mixed or a pure unmixed behavior, right? But you'll approach one or the other, and that's the solution you should use. All right, and the last geometry we want to talk about is shell and tube. So these are pretty common heat exchangers. In a shell and tube heat exchanger, I'm not sure which one to look at here. You take a bundle of tubes, right? So this is a big bundle of tubes, and you insert them in the shell, right? So what happens then is you bring fluid in at the end of the shell and tube heat exchanger, and you give that fluid, in this case, you give it access to some of the tubes, right? So that fluid flows through the tubes. Depending on how many passes it is, you get to the end, and you turn it around and you bring it back through the other tubes, right? So that's the tube side heat exchanger. And then the other fluid you bring in on the side of the shell, and you cause it to flow around the outside of those tubes. So that's the shell side fluid in the shell and tube heat exchanger, right? And one thing that you can see is that you don't just bring the fluid in on the shell side and then let it leave somewhere else in the shell side. You actually put in some kind of baffles so that you're forcing the flow to go across all the tubes, turn around, go across all the tubes, like this. So you end up with a heat exchanger that looks a lot like a bunch of cross-flow heat exchangers that are somehow plumbed up almost in series, right? So it's some combination of a cross-flow and a counter-flow heat exchanger, depending on how it's put together. You can see that again here. In this case, you bring the tube side fluid into here, it goes through all the tubes, and then it comes out over here. You bring the shell side tube fluid here, and it goes across the tubes back and forth until finally it makes its way out here. This is just a schematic of it, right? You bring the tube side fluid here, it goes through all these tubes, and you bring it out. You bring the shell side fluid here, and it goes back and forth until it comes out. And these things you'll see when you look at the solution are classified based on the number of tube passes and the number of shell passes. Right, so the number of tube passes is just does it go through all the tubes in one pass and come out? That's a single pass heat exchanger. Or does it do something like this, where it goes through half of the tubes and then turns around and comes back in a second pass and goes through the other half? That would be a 2-pass heat exchanger. You could also have a 4-pass or an 8-pass heat exchanger, where it's going through kind of a quarter of the tubes, back, right? So all different configurations that are pretty cool, because it lets the same basic physical device deal with more applications, right? You can take this basic physical device and by putting different headers on it, you can cause it to have a slightly different performance, right? On the shell side, you can do something similar, right? So this is a 2-tube pass heat exchanger. This is a 2-shell pass heat exchanger, where you bring the fluid in on the shell side and you make it go back and forth over half of the tubes. When you get to the edge, you make it go back and forth over the other half. So that's a 2-shell pass heat exchanger, right? All right, so those are the different geometries of heat exchangers. We will get into how to analyze heat exchangers in upcoming lectures. But the other things that we need to talk a little bit about are two things that you can do to a heat exchanger no matter what the geometry is, no matter what the configuration is. I can do an overall energy balance on my heat exchanger, right? This is something you did in thermodynamics. We just draw a control volume that goes around the entire heat exchanger like this. And we basically say, we're going to assume the heat exchanger is completely insulated externally. Its jacket is insulated, so that whatever energy is lost by the hot fluid must be gained by the cold fluid, and that's the heat transfer rate, right? So that's this equation here. We're using, again, I for enthalpy because H would just be too confusing. One of the assumptions that we've obviously made right here is that the jacket is insulated, right? If I want to go from this equation to the next equation, which is the one we typically use, I'm making another couple of assumptions, basically related to how enthalpy is behaving. I'm assuming that enthalpy can be written as specific heat capacity times temperature. So that actually does a bunch of things. It says that I'm ignoring any pressure-driven enthalpy changes, right? Enthalpy actually is a function of pressure. I'm ignoring that as being small. And it also says that the specific heat capacity is constant, right? Those are assumptions that should be checked, and they're not always very good assumptions, right? But if you can make those assumptions, then this is the equation you have. And basically this is saying that the heat transfer rate is equal to how much enthalpy change is experienced by the hot fluid. That's this equation here. It's also equal to how much enthalpy rise is experienced by the cold fluid. That's this equation here, right? This big C dot is just shorthand for m dot times C. This is the capacitance rate. So this is C dot H. That's the capacitance rate of the hot fluid. It's the mass flow rate of the hot fluid times the specific heat capacity of the hot fluid. And it's just a shorthand so that we don't have to write these two things separately. The capacitance rate of the hot fluid. It has units of watts per Kelvin. And actually that's kind of how you should think about capacitance rate. It's how many watts of heat transfer rate do I have to put into this stream of fluid in order to get its temperature to rise by 1 Kelvin. If I have a big capacitance rate, I'm going to have to put in just a ton of heat in order to change its temperature. If I have a small capacitance rate, like just a little trickle, a little bit of heat's going to change its temperature a lot, right? If I have a fluid that is evaporating, a pure fluid that's evaporating at a constant pressure, that's a case where I can put energy into that fluid and its temperature won't change at all, right? That's a capacitance rate of infinity, right? So that's getting to the highest capacitance rate you can have. All right, so these are equations that I can write down for any heat exchanger. They don't help me solve the heat exchanger problem because, if you think about a typical heat exchanger physical situation, I would have a heat exchanger, I would plumb it up to some hot fluid at THN, I would plumb it up to some cold fluid at TCN, and I would want to know what TH out is and what TC out is. And if you look at these equations here, this is two equations in three unknowns. I don't know Q dot and I don't know the outlet temperature. So these are true equations. They're just not sufficient equations for me to actually solve and predict the performance of a heat exchanger. To predict the performance of a heat exchanger, I actually have to dive inside of this heat exchanger and do two things. The first thing I have to do is figure out how well thermally connected is the hot fluid to the cold fluid, right? Geometrically inside of here, I have a bunch of thermal resistances that separate the hot fluid from the cold fluid. I need to understand how good that heat exchanger is. A good heat exchanger will have a small thermal resistance between those two fluids, right? So that's one thing I can do. And then the second thing I have to do is couple that understanding of the thermal resistance between the fluids with energy balances on the two fluids, right? So let's talk about the first thing. which is the conductance of the heat exchanger. So the conductance of the heat exchanger is just the inverse of the total thermal resistance that separates the hot fluid from the cold fluid inside of this heat exchanger. And calculating this total thermal resistance is basically an exercise in all of the stuff we've learned so far in heat transfer, right? You have conduction resistances, maybe you've got some fins. Certainly you probably have some convection resistances, right? And you have to sit down and actually calculate or estimate these things and then add them up appropriately to get the total thermal resistance. This tube-in-tube heat exchanger is a very simple example, right? If I was going to go from the hot fluid to the cold fluid in this tube-in-tube heat exchanger, I would certainly have a convection resistance between the hot fluid and the outer surface of this tube, or convection hot. I would have some conduction resistance across the tube shell, right, the tube wall, or conduction. And then I have a convection resistance between the inner surface of the tube and the cold fluid. That's our conduction, or our convection cold. I would add those up together and I would get the total resistance. The inverse of the total resistance is the conductance. A good heat exchanger is going to have a small total resistance. It's going to have a really big conductance, right? Those get to be bigger, more expensive, higher performing heat exchangers. One thing about heat exchangers, a couple of things about heat exchangers that make them a little bit more complicated than what I just said is, first of all, you can have what's called fouling that you need to think about. And second of all, rarely is the geometry as nice and straightforward as what I've drawn here. So let's talk about fouling first. Fouling is basically referring to the fact that as you operate these heat exchangers longer and longer, so if I put this into service and let it run, I might be letting it run for years and years and years. And what happens is your heat exchanger has all this surface area, right? It needs to have a ton of surface area in order for it to work. And so having all that surface area is also the spot in your system that's most likely to accumulate crud. And that crud is going to build up on the wall, and it's eventually going to cause an additional thermal resistance between the hot fluid and the cold fluid. And you need to account for it, or at least think about it, right? And so you just basically add fouling resistances into your network. So here I've got convection from the hot fluid to the wall. Here I've got an additional resistance related to fouling of that wall. And then conduction, and then, convection from the cold fluid wall to the cold fluid, but then an additional resistance that's related to the buildup of fouling on that cold fluid wall. And the way that you calculate a fouling resistance is you have what's called a fouling factor. That's this R double prime F. And this is something that you typically go look up. I have a certain kind of fluid, right? And it's been treated in a certain way. What kind of fouling factor am I going to have? And this is usually given to you in something like meters squared Kelvin per watt, right? And I then divide that by the area that's being fouled. Right, so a bigger area is going to give me a smaller fouling resistance. This looks a lot like a contact resistance, right? It's the same kind of an idea. So there's different ways to get fouling factors. One way is you look in ease. So if you go to options, function information, let's go to fouling factors. You can see just a list of these things, right? And this is basically just taken from a couple of different handbooks. And if you look at how this is put together, it's based on what kind of fluid do you have. So here is a bunch of fouling factors for water. Where's my little... Oh, I can't do that here. Never mind. Sorry. Here's a bunch of fouling factors for water, and then the different ones are for the different way that the water could be treated. So brackish water sounds horrible. That's basically untreated water. City water... right? And then you go all the way to, water that's been treated, so closed loop treated water and so on and so forth. And you have engine oils and other different types of fluids. So, I'm not sure that you can take these as being incredibly precise, but they are based on some data, and they would give you some indication as to how big those fouling resistances can be. And of course, like anything, once you understand how big they can be, you can decide whether you need to think about them, or you can sort of not worry too much about them because they won't really affect your answer that much. All right, so let's go back here. That's fouling. The other thing you got to understand is that most heat exchangers are composed of geometries that aren't simple internal flow geometries, right? So you might have flow over banks of tubes, right? Well, that's not an internal flow or an external flow, right? You have something that looks a lot like external flow over a tube, but these tubes are interacting in terms of the boundary layers, so it's also kind of an internal flow. It's not a straightforward geometry, so you're going to be going off and looking for basically empirical correlations for flow over that kind of a geometry, and that exists in ease. I guess I'll show you. If you go to options, function information, this is under convection. It's got to be either under internal flow or external flow. We put it under external flow, and I think if you go way over to the end here, oops, yeah. So there's this is one type of tube bank arrangement where the tubes are in line. This is one where they're staggered, but this is where you would get that kind of information. And you guys got to understand, this is from work that people have done, basically measuring the performance of these kinds of flows, right? The other kind of flow you'd get that is not flow through a tube the way you normally think of it is you could have flow longitudinally along banks of tubes, right? And there's correlations for that. Any of these cross-flow heat exchangers typically have some kind of very tortuous, weird path, right? So if you think about what's going on here, we have flow through these fins. So these are plate fins that have some kind of corrugations to them, but then also over the tubes, right? So these are tubes inside of here that the flow has to go over. So this is, some aspects of flow through a duct, some aspects of flow over a tube. Obviously it's a complicated situation. And the correlations for these compact heat exchangers traditionally have been obtained. The data, the solutions have been obtained using what are called compact heat exchanger correlations. So these are basically just measurements of the performance of different geometries, right? And so here's an example. This is a very specific geometry, FC tubes S8038T, right? This is a geometry you can go buy that is a fin-to-tube geometry. And the performance is given to you in terms of a bunch of things. Up here you've got some geometric parameters about this geometry that are useful. So you might have something about how much of the area is fins versus how much is not fins. So 91.3% of the area in this heat exchanger are the fins. What's the hydraulic diameter of these flow passages? This is what's the open area to the open area of the core to the approach area. So basically the area that I see when I'm flowing through the heat exchanger is 53.4% of the area that I see as I'm flowing towards the heat exchanger before I get into it. And then this is the specific surface area. So this is how much surface area do I have per unit volume of heat exchanger, right? So these are all geometric parameters. And then this F and J, these are the non-dimensional pressure drop and non-dimensional heat transfer, right? So F and J, and you have to understand how those things are defined. One thing that's actually really cool in these, you won't appreciate until you try to do a heat exchanger calculation with one of these, is these libraries have been put into ease. So if you go to compact heat exchanger, you will find that there's a bunch of different functions here that you should be aware of, right? So one is just the geometry. So here, if I go up here, I can scroll through these different geometries. And what this is going to give me back is literally just what is the hydraulic diameter? What's the fin pitch? What is the specific surface area? So what are the geometric characteristics of these different kinds of heat exchangers? If you go down, you do have ones that give you back the F and J factors, right? So here, this is going to give you the F and J for this particular geometry as a function of Reynolds number. That requires that you then understand how Reynolds number is defined, how F is defined, and how J is defined, which is, fine. You can do that. But if you go down a little bit farther here, you're going to find that the coefficient of heat transfer can be given back to you, right? So if I click on this, you'll see that, it basically is doing the uncoupling or the computation that will finally use the J factor to give you that heat transfer coefficient, right? So it's it's decoding that for you, right? Which is really convenient. And if you go down even farther, same thing for the pressure drop, right? So if I click on this, here I give it my heat exchanger, how big it is and everything like that, and it gives me back delta P. So it's decoding the F factor for you, right? And I don't expect you to know these. I don't expect you to, be an expert in the compact heat exchanger library, but I want you to understand where they are. Because it's extremely likely that at some point in your career, you will be either simulating or sizing or something with a heat exchanger core that looks like this heat exchanger core, right? And so you kind of have two, maybe three different possibilities in terms of how you proceed. One is you just trust the manufacturer and you go to the manufacturer and say, hey, I need to do this job. What heat exchanger should I use? That's an iffy proposition, I'd say. Two is you take a little bit of data to try to understand how this thing behaves, and then you try to use that data to go off and do other things. That's a very expensive proposition. Three is you look at the geometry and say, this looks really a lot like an S8038T geometry. So I can simulate that using the compact heat exchanger library, using the J and F factors for that particular geometry, right? And that's, I think, a much more realistic thing to do and a much more powerful thing to do that a lot of people probably can't do. All right, so that's an introduction to heat exchanger, the different configurations, what fouling means, and then at least an introduction to some of the ways that you might have to go get the UA, the conductance. What we need to do next is start looking at, okay, I have a heat exchanger, I know the conductance, right? I figured it out, I know the overall energy balance. I got to dive in now and actually do an energy balance, a differential energy balance on each of the two streams and solve that resulting set of coupled differential equations, right? It could be coupled ordinary differential equations, right? So if we go back and look at the temperature distribution for a parallel flow or a counterflow, this temperature, it's only changing in one dimension. This temperature is only changing in one dimension. That's going to give me two ordinary differential equations. And these are the ones we're actually going to solve because they're easy enough to solve. But if you look ahead, some of these heat exchangers, that's a two-dimensional temperature distribution, and this is a two-dimensional temperature distribution. In order to solve a cross-flow heat exchanger problem, you'd have to solve two coupled partial differential equations, right? Which we're not going to do in this class. But actually it's laid out in the book how you can get these solutions as well. So that's the next thing we'll do in the next lecture.